Okay, let's see if I can fit in the frame here. Alright, so I'm going to demonstrate my program, the client-server architecture program. It runs in Python 3.10. And so first we open the server file, which is in documents. And here is the code. How this works is explained in a report. And we run this file. So it says waiting for the client servers to join. So in a regular client server architecture, you have a server with a constant IP address, which is true. This one has a constant IP address. And you have clients which can have variable IP addresses. And they make requests from the server, which then responds. In this case, I've employed a hybrid architecture, which does something rather interesting, which I'm now going to show. So in mathematics, there's oftentimes you have calculations that are too difficult for a single computer to execute to any degree of efficiency. So in this case, the server is able to distribute work to the clients in order for them to help out. So in this case, we're going to name the first computer Alice, and it's connected with Alice, as you can see here. We're going to name the second computer Bob, and now we have both computers. But let me open these windows and put them in a position so you can see them both at once. Okay, now what this calculation, this program does is numerical Riemann sum integration of a polynomial. And of course you could use other functions. One's more difficult to integrate, but polynomials are well understood, so I chose this. But to numerically integrate a function of arbitrary nature, you have to compute a ridiculous number of summations, and having a single non-parallel processor sit there and execute a list of summations is not easy at all. As a result, it's best to distribute the work, and this server client, well, really it's a hybrid architecture, but it's based on the founding principles of the client-server architecture, is able to distribute the work, combine the results, and perform a useful calculation across what could be 3 computers. This video shows them all on one computer. I will put a subsequent video up which shows it being done on the 3. Let's see, look at that. Okay. So, let's say we wanted to have a third order polynomial which had a constant term of 1, linear term of 2, the second order term, squared term of 3, cubic term of 4. We're going to want it to integrate between 10 and 25, and this is the differential of a tiny number used in between them. We're going to use 1/10,000th, and then watch carefully what happens next. This computer is given half the integral range, and then this computer is given the remaining half. When this happens, so this one's given half, and then this one's given half, and each one computes sum, part of the integral, which is this number here and this number here. These are sent back to the server, which then combines the result, and it comes up with 395,795 point decimal 67 . So now let me verify the work here, and let's see, can you guys see that? So you can see the result it gave here, 395,795. So what we can do is we can use our trusty TI calculator and enter the numbers in. So the range was from 10 to 25.00 of that polynomial, 4x cubed plus 3x squared plus 2x plus 1 dx. And the answer the TI calculator obtained, so 395,795, was the answer this program gave, as you can see there. And the answer my calculator gave for the same integral, 395,790. So it's remarkably close. 395,790. So this is the modified client-server architecture program, and of course, if you wanted to, the server allows you to take another integral. So what we could do is we could then integrate some other arbitrary function, a zeroth order polynomial. That's pretty easy, a constant times the range based on fundamental theorem of calculus part 2. The constant term could be 10. We're going to want to integrate it between 0 and 15, so it should be 150. Use a small number for the differential. And if we look at our client servers here, and I know I'm skewing the terminology, but you can see this one distributed half the range, this one distributed the other half of the range, each one computed 75, the final answer is 150, which is 15 multiplied by the 10 as mentioned. So it is possible to distribute computing between multiple computers, and although this is on one local network, I will show this on multiple laptops. Anyhow, this is my client-server hybrid architecture demonstration of parallel computing. I was going to mention, I'm sorry, I turned it off. I was going to mention Amdahl's law and the limitations of parallel computing, which includes the step that combines the result, or the steps that are dependent upon knowing all of the results. In other words, Gene Amdahl, a computer engineer in the 1960s, determined that you can only speed up things by so much using parallel computing, because you can only achieve advances in the steps that can be done separately. And those steps that involve all the results being known at once are harder to speed up. Anyways, thank you for watching, and I made this video to demonstrate my work.